Welcome to AI Paper Slop. We are diving straight into the paper today, which is called GRAIL Generating Humanoid Loco-Manipulation from 3D Assets and Video Priors from researchers at NVIDIA and UCLA.
Right. So to give you the core insight right out of the gate, scaling humanoid loco-manipulation data is totally bottlenecked by the physical world right now.
Yeah.
I mean, teleoperation and motion capture are limited by hardware setups, and trying to reconstruct in the wild video is plagued by ill-posed depth and scale ambiguities.
Which is a nightmare.
Exactly. So GRAIL's solution is a fully digital data generation pipeline. They compose known 3D assets into a simulated scene, use video foundation models, or VFMs, to generate the interaction video, and then reconstruct perfect 4D human-object interaction trajectories.
Wow.
And the output is over 20,000 loco-manipulation sequences. They use these to train task general tracking policies using a pre-trained whole-body controller called Sonic.
And the results?
The result is zero-shot sim-to-real deployment on a physical Unitree G1 humanoid, hitting an 84% success rate on diverse object pickups and 90% on stair-climbing.
That is massive. So if you are building embodied AI right now or, working anywhere near sim-to-real pipelines, this paper is basically a blueprint for entirely bypassing physical data collection.
It really is.
But to understand why the GRAIL pipeline is such a breakthrough, we first really need to look at why current data generation methods are just failing to scale.
Right, because historically, getting a humanoid to do anything means you need demonstration data, and we've been stuck between two pretty bad options.
Yeah.
First is physical collection. So you set up teleoperation rigs, like the Aloha systems, or you shove human actors into those heavily instrumented mocap suits.
Right, which gives you great data, but
the friction is just unbelievable. I mean, for every single new task or novel object or even a minor room change, you have to manually reconfigure the physical scene.
it's basically artisanal data collection at that point.
Exactly. It completely fails to reach the volume that modern foundation models actually demand.
So then, naturally, the field pivoted to the internet.
Yeah, scraping millions of hours of YouTube videos.
Right, trying to reconstruct 4D metric environments from random human interactions. But that approach runs into a complete mathematical wall.
It creates a totally ill-posed inverse problem. When you give a neural network a flat, monocular RGB video from YouTube, it has no idea what the underlying physical reality is.
Right.
It doesn't know the camera extrinsics. It doesn't know the true metric scale of the room. And it has to literally hallucinate the exact 3D geometry of whatever object the person is holding.
It's like trying to bake a cake by watching a blurry video of a bakery from across the street.
That is actually a great way to put it.
You can guess the general shape of things, but without knowing exactly where the camera is, the actual metric scale is just a complete guess.
Right. Standard video reconstruction just leaves the model guessing at the physics. But GRAIL succeeds because they basically rig the matrix.
Yeah, they don't guess at all. They start with a fully specified 3D configuration.
Exactly. The authors call it a privileged setup. Step one is procedural scene assembly. They use Infinigen, which is an open source generator, to build a perfectly mathematically defined simulated environment.
Like a floor-only room or maybe a room with a table.
Yeah. And then they drop in a 3D object asset and a 3D human asset into that space.
And we should point out that human asset is pre-fitted to the Unitree G1's morphology, right?
Yes, that is a huge detail. They ensure the human's limb length match the robot's hardware right from frame one.
Which saves them from those massive retargeting headaches later on.
Oh, absolutely.
Yeah.
Mismatched morphologies are just a notorious source of compounding errors in robotics.
Right, so they have the assets in the room. Then what?
Then they use a rigid body simulation to just let the object drop and settle naturally onto the table or the floor.
So no floating objects or clipping errors.
Right. Then they render the very first frame of this scene. And because they built the digital world, they know the exact camera, intrinsics, and extrinsics, down to the millimeter.
They hand that perfect initial frame to a vision language model to get a text prompt and feed both into Kling 2.5 Turbo Pro, which is the VFM.
Right. And Kling outputs a super realistic static camera video of the human interacting with the object.
So for the researchers listening, the elegance here is that by controlling the initial 3D state, GRAIL turns an ill-posed inverse problem into a highly constrained optimization problem.
Exactly. But, a 2D video doesn't move servo motors.
Yeah.
Step two is extracting the 4D metric trajectories.
Right. We need the exact math of the movement.
So initially, they run independent tracking models. They use GNMO for the per-frame SMPLX body pose.
Which gives them the human body mesh.
Right. Then Wheeler for the Mano hand poses, and a fine-tuned foundation pose for the 6-dove object tracking.
Okay, wait, I have to push back here. I've used Foundation Pose, and it is incredible at tracking objects. And if Gino and Willer are so good at body and hand poses, why do we need this massive joint optimization phase they do next? Can't we just slap those tracks together?
Visually, it might look okay to a human, but physically, it is a complete mess for a robot.
Really? How bad is it?
The failure modes are catastrophic. You get floating contacts where the tracking says the hand is holding a cup, but the 3D hand mesh is hovering like 2 inches away.
Oh yeah, that won't work.
You get severe mesh penetration where fingers clip straight through solid objects, and worst of all, you get depth scale drift.
Right, because monocular tracking algorithms process the human and object separately.
Exactly. So the object mathematically slides back and forth in the z-axis, completely independent of the human's actual movement.
Which is a nightmare. I mean, if you've ever tried to map human mocap data to a robot, depth drift is the enemy.
Totally. So to fix this, they freeze the hand poses from Euler because they're locally accurate, and then they optimize the residual motion parameters of the body and the object over all frames simultaneously.
Using a joint loss function.
Yes. The key point and projection alignment terms are standard, just keeping things visually consistent with the Kling video. But the physical alignment terms are where the magic happens.
Let's deep dive into the depth alignment loss, because this relies entirely on that privileged Infinigen setup.
Right. Because they generated the scene, they have the ground truth background depth map.
Which is huge.
Yeah. So they use Mogi 2 to get a relative depth map of the interaction, and SAM2 to segment out the human and the object.
They unproject those segmented pixels into 3D point clouds, right?
Exactly. And the loss function aligns those unprojected point clouds to the known metric scale background depth of the Infinigen scene,
Anchoring the whole interaction into true physical space.
It completely eliminates depth drift.
Okay, but what about the fingers clipping through the object? How does the math stop that?
That is the contact alignment loss. First, a vision language model tags frames, saying, for example, the left hand is making contact.
Okay.
When the loss function sees that tag, it penalizes depth discrepancies, but only for the object vertices that overlap with the contacting body part in screen space.
Oh, wow. So it forces the depth of the hand mesh and the depth of the cup mesh to perfectly equal each other right at those overlapping vertices?
Yes, it mathematically snaps the surfaces together at the exact point of contact.
Without letting them phase through each other. That is so clever.
And this pipeline is heavy. It takes about 14 minutes per sequence on a single A100 GPU, and 8 of those minutes are just for this joint optimization.
So now we have over 20,000 perfect 4D human-object interaction sequences.
Yes.
But stepping back, how do we actually map those human mesh movements into torque and joint commands for a 43 degree of freedom Unitree G1 robot?
That is the core sim-to-real challenge. And GRAIL doesn't start from scratch here. They use Sonic, which is a pre-trained whole-body controller, as their foundational prior.
Instead of fitting one controller per sequence, which is what a lot of older methods did.
Right, doing that is super inefficient. Instead, they train task general trackers across whole families of behaviors using proximal policy optimization, or PPO.
Which takes some serious compute. They ran 30,000 iterations on 64 NVIDIA L40 GPUs, taking like 30 hours.
Yeah, it's a massive training run. And they create 2 distinct specializations. The first is the object-aware latent adapter, which handles manipulation.
Things like picking up objects.
Exactly. And the crucial architectural choice here is that they freeze the sonic encoder and decoder.
They freeze the locomotion base. That is such a smart insight.
It really is. You don't want the robot forgetting how to balance just because it's learning to reach for a coffee cup.
Right. So the effect upper runs in parallel.
Yes. It takes in proprioception, so the robot's awareness of its own joints, and a basis point set, or BPS, encoding of the object shape.
And for the ML folks listening, BPS is such a game changer here. Processing raw point clouds is so slow, but BPS creates a fixed length encoding by measuring distances from fixed points to the object surface.
Exactly. It gives the network a highly efficient mathematical representation of the object shape and where it is relative to the hands.
So what does the adapter actually output?
2 things. First, a 64-dimensional latent residual, which gets added into the controller stream right before FSQ quantization.
So it's subtly whispering corrections to the locomotion base, shifting the center of mass without overriding the balance logic.
Precisely. And the second output is a 2-dimensional binary hand primitive, basically just an open or close command for the gripper.
Right, for the final grasp. So that's the manipulation side. What about the scene-aware tracker?
That one handles terrain, like stairs or slopes, and sitting down. For this, they do fine-tune the base controller, but they add an 11 by 11 local height map.
Processed by a 3-layer CNN encoder?
Yes, it acts as a real-time topographic map of the ground right under the robot's feet.
I want to circle back to the manipulation reward functions really quickly, because they are incredibly specific. They didn't just use a sparse reward like, did the robot touch the cup?
No, sparse rewards cause sloppy behavior. They engineered highly specific math for a successful grasp. First, sustained contact time.
To make sure the grip actually holds.
Right. Second, opposing direction of the thumb and index finger. It heavily encourages a pinch grasp rather than just swiping at the object.
And the third one?
Proximity to the contact centroid. It penalizes the fingertips if they stray too far from the exact intended grasp point on the BPS encoding.
It literally forces the simulated hand to wrap around the specific geometry.
Yes.
Okay, so the architecture is brilliant, the optimization is great, but how does this survive the reality gap?
Well, the simulated benchmarks set a very high bar. On a 124 motion benchmark, GRAIL hit an 81.4% success rate.
Which completely crushes the baselines. HDMI was at 48.5% and Rhythmic was at 49.2%. GRAIL nearly doubled them.
Yeah. But for the real-world deployment, they distill these tracking policies into egocentric RGB visual policies.
Because the real robot isn't using external mocap cameras.
Exactly. It's just using a Luxonis OKDW camera on its head, running inference at 10 Hz and streaming to an RTX 5090 desktop.
And it actually works on real hardware.
It works beautifully. They hit a 90% success rate on stair climbing.
90% on a bipedal robot using an RGB policy trained purely on generated digital data. That is wild.
And 84% on diverse object pickups. What's amazing is that it generalized to completely unseen objects, hitting 80% on things like wet wipes and lint rollers.
That really proves the BPS encoding and the latent adapter are learning the underlying physics, not just memorizing the coordinates of a training object.
Definitely. But, it is vital to understand the edge cases here.
Because the whole system is completely at the mercy of the video foundation model.
Yes. If Kling generates inconsistent textures, or if the human hand morphs into the object, which generative video still does, Foundation Pose immediately loses tracking.
So how does GRAIL handle that?
They have an active filtering step. If the SAM2 segmentation mask tracking error exceeds 0.2, they just throw the entire sequence out.
Basically recognizing it as a hallucination.
Right. And it also struggles heavily with severe occlusions, like if the object gets hidden behind the human's torso.
Sure. So zooming out, GRAIL proves you can use generated video to train a physical robot, but it leaves us with a really provocative theoretical question for the future.
It does, because GRAIL relies entirely on VFMs, and those are trained on massive data sets of human internet video.
Right.
So we are using human priors to generate physical robot data. But as robots like the Unitree G1 get deployed and start generating petabytes of their own real-world autonomous data, will the next generation of embodied AI even need these human video priors?
Are we currently watching the bridge being built that will eventually make human-centric video foundation models totally obsolete for robotics?
It's a massive question for the field.
Definitely something for you to ponder as you look at your own sim-to-real pipelines. Think about how asset condition generation might help you bypass your current data bottlenecks. Thanks for tuning in to this deep dive on AI paper slop. Keep building and keep questioning the data.